All right, the concept of torque. In engineering, they call this moment. I'm not sure why we choose different names for it, but it is the same thing. Torque, we use the symbol tau to represent. It is a vector. The fundamental equation for torque is R crossed with F. This is called the cross product. This is specific, another way to multiply vectors. If you remember before, we talked about work, and work, at least if force was constant, work was force dotted with displacement. The dot product multiplied parallel components of the vectors. It gave us a scalar answer. So as we were solving problems using work, we only cared about the component of the force along the direction of motion. So the force causing the motion, these multiplying parallel components accounted only for the components of the forces that were in the same direction. And we could generically write the dot product as the magnitude of the force, that magnitude of the displacement, times the cosine of the angle between them. The units, of course, newtons times meter, we called a joule. With the cross product is fundamentally different. The cross product multiplies perpendicular components. So we need the components that are not in the same direction. The answer is a vector. And that answer, that vector, is perpendicular to R and F. We can generically write the magnitude of the torque as the magnitude of R, the magnitude of F, times the sine of phi, where phi is specifically is the angle between R and F. Now, I don't recommend blindly using that equation as written. Make sense of what you're doing as we talk about problems, which I'm going to walk through this concept of torque. I will show you how to do the cross product in a separate video. We're going to talk about what we mean by the cross product and look at what we mean by torque in this video. Now, units, though, of torque. R is what we call a lever arm. It is a distance. It will have units of meters. Force, newtons. So we are ending up with Newton meters again. But this is not a joule. That's all sorts of confusing, right? So work, Newton times a meter, we called it a joule. But remember, work was a transfer of energy. We either put energy into a system or took it out. Torque in and of itself is not transferring energy. It can cause an object to turn, potentially, but it doesn't have to per se. In order to turn this into an energy, the torque needs to be applied over some sort of distance. So to turn this into work, we would need the torque, but then that torque would need to be applied as an object rotated through some angular distance, theta. So a meters times a Newton times a radian is what's going to give us the joule. The joule will come from the newtons times the meters times the radian. Though technically the radian isn't a true unit, so we wouldn't necessarily write it. But just keep that in mind, because you're going to want to make torque energy or joules at first at least. So torque in general. We can think of torque as a turn or a twist. So some sort of force causing rotation. But it's not just the force. That force has to be applied in a very specific way. This is something that you are totally familiar with. You may not realize it, but you are, I hope. You all have opened doors in your life. So if I have a door, the hinges are over here. The doorknob is over here. We say the rotation axis goes down through these hinges like this. So the rotation axis is a line, essentially is these screws or bolts that go through the hinges holding them in place. So the rotation axis. Now I hope you remember, if you haven't even accidentally done this, you cannot open a door by pushing on the hinges. Right? If I come up to the door and start pushing against these hinges, P for push, the door's not going to open or shut. Okay, another way we cannot open a door by pushing inwards on the edge. Meaning if I came to this other edge of the door and I just pushed on the edge inwards towards the hinge, if I push that way, I will not open the door or close it. I will not cause the door to rotate. Both of these cases mean there is no torque. If I do not cause rotation, then I have not applied a torque. Okay? So torque is not just a force, it's how I apply the force. I think we probably know fairly intuitively that if I push inwards towards the door, on the edge opposite the hinges, this is the most effective way to open or close a door. Meaning the biggest or best torque. I could push somewhere in the middle, still towards the door, And it would still open the door or close. Just not as effectively as pushing against the opposite edge. So there is a torque, but it's not as good as the torque when we apply the force along the edge or over opposite the hinges. Okay. Torque depends upon where we apply the force and how, meaning relative to the door. So if you remember, pushing inwards on the edge was different. I can't open or close the door by pushing in towards the hinges on the edge, but if I push on the edge towards the door, then I am most effective at opening or closing the door. So how the force is applied is important. Okay. Let me draw this from a different vantage point. So a view from above. So if this is our door, we're looking down, so we're only seeing the top edge of the door. The rotation axis, I'm going to call it RA for rotation axis, would be on that left edge. That's where those hinges are. Now the force I apply, if I try to push exactly at the hinges, then I know I do not produce a torque. I do not make the door open or close. So no torque there. If I push in this way, I don't make the door open or close that way either. It turns out any force that is directed towards the hinges will not produce a torque. That means if I decided to apply a force at some sort of angle, this force has a component that points towards the door and a component towards the hinges. This component here, this F, no torque due to this component. The component that's perpendicular to the door, this component creates the torque. And again, torque, I just mean this component is going to make this door rotate around its hinges, assuming nothing else is in the way. Okay. This force causes the rotation, thus it is creating the torque. When we say torque, I don't write my taus very well. The torque is equal to R cross F. That is the vector equation. You're going to see in the test notes as well, I can't remember which one they put the perpendicular sign on, the R or the F. The cross product is multiplying the components of the vectors that are perpendicular to each other. That's what this little symbol means, the perpendicular component. It doesn't matter which vector we break down into perpendicular and parallel. R, the lever arm, always points from the rotation axis to where the force is applied. So if I come into my picture, I would draw this R right here. I start it at the rotation axis and I draw it over to where that force is applied. Notice this component of force creating the torque, this is 90 degrees. That's what we mean in our equation over here, saying torque is equal to R, that lever arm length, times the force that is perpendicular to it is going to give us the maximum amount of torque, the most effective torque. I know, and we probably all know, just kind of from experience, that pushing perpendicular to the door near the end gives us the most effective torque, the biggest torque. It's easiest to open the door by pushing at that end. And again, that's because we've maximized R, the lever arm, and we are pushing perpendicular to the door. So the torque in this case would just be the width of the door times that push, P. Now this particular push on the door would cause the door to start rotating this way. That would be counterclockwise, opposite the way the hands on a clock travel. We abbreviate this a lot of times as CCW, counterclockwise. That's different so same door, same hinges, same push, only if the push comes from the opposite side, the door would rotate the opposite way. It would rotate clockwise. So CW is the way we represent this. Now, technically, this is tied to our coordinate systems. If we have just a typical Cartesian coordinate system where X is to the right, Y is up, Z would come out of the screen. That is called a right-handed coordinate system, meaning if I take my right hand and I put my fingers in the direction of X originally and bend them towards Y, then my thumb represents the Z-axis, meaning coming out of the screen. Now, you have to use your right hand. This is called a right-handed coordinate system. Coming back to these torques, if I let my fingers of my right hand follow the direction of travel. So pretend my fingertips are representing this arrow right here, and I let my fingers follow with my fingertips right here, representing the arrow. My thumb points out at me. This would be the Z direction if we were using this coordinate system I just mentioned. Counterclockwise would represent the positive Z direction in this coordinate system. Now that's a little weird. When we talk about like velocity being in the X direction, we know an object's moving in the X direction, to the right. these directions just represent the rotation axis. So it means this rotation axis, these hinges essentially point at you, and this force makes the door rotate counterclockwise from your view. That's what that means. In the right-hand picture over here, we would say that the torque was in the negative z direction. Again, if I let my fingers of my right hand follow this path, and these are the tip of my fingers. To get my fingers following that path, my thumb points away from me. That means the Z direction, or into the screen, away from me. But again, that just means counterclockwise. That means if we were looking at the rotation axis with our thumb pointing inwards, we would see rotation going clockwise around that axis. So in general, it's fine for us to leave and talk just about clockwise versus counterclockwise, since we're just dealing with our two-dimensional picture here. We will not be doing much in terms of Z direction. You get to do that in statics and dynamics, which is actually fun in my opinion, because that's what I enjoy doing. Clockwise, counterclockwise, though, we do need to account for those differently. The door rotating clockwise around its hinges from this view is different than the door rotating counterclockwise. One way would open, one way would shut. In either case, though, the torque is biggest when these forces are perpendicular to the door and as far away from the hinges as possible. So when we say the cross product, so the generic form of the torque equation, torque is R cross F, the cross product is multiplying those perpendicular components. So that's what we're seeing here. We get a maximum torque when the angle between our force and lever arm is 90 degrees. If we come back up to the top left picture, when our force was not 90 degrees, this big old angle right here, that angle is actually also the same as taking the sine of this angle inside. I'll call this phi1 and phi2. If I have this force push, this force times the sine of the angle is going to give me this side. It's going to give me this component that is perpendicular to the door. That's why we can write generically torque as RF sine phi, as long as phi is specifically the angle between those two. In this picture, sine of phi1 is the same thing as sine of phi2. So measuring all the way from the door over to the force and taking the sine of that angle gives us the same answer as taking the sine of the force to the extension over here of the door. If we use this equation, though, we have to make sure that angle phi is between R and F, those vectors. So we will be writing and drawing pictures that represent R and F every single time. So similar to the force section where we drew free body diagrams, we will be drawing free body diagrams again. We will need to represent in our picture as well, though, the R, these lever arm vectors, to account for the R, to be able to figure out the angle between R and F. Because the torque, the turning, the ability to open or close a door, for example, is all about where we apply the force and how we apply the force. So for some reason, the calculations tend to throw students off. I am not entirely sure why. Quite honestly, I think we psych ourselves out. We are all familiar with opening and closing doors. And that's why I use that example, right? You know how to open a door. You know to not run up and push on the hinges. You know to push perpendicular to the door, opposite the hinges. So conceptually, you have an understanding of torque. We're going to build and look at solving problems involving torque as well. And just fair warning, for whatever reason, it tends to be confusing for students. And again, I'm not entirely sure why. So remind yourself that you have a conceptual understanding of this. Torque is just the ability to make something turn around hinges, to turn around an axis. So opening and closing a door, remind yourself you're familiar with that. So I'm going to go through some conceptual questions and a problem, and then some examples of what we call equilibrium.